PPT screen which is coming over your PPT screen.
Give it.
You can close that from now. It's okay.
Okay. Okay, sir.
Yes, it's okay. Please go ahead.
Sir, this is the content page where I first do the introduction, graphene, role of functionalization, sensor, research gap, why controlled thin film are essential, Langmuir Blodgett technique, deposition, isotherm graph, preliminary work, references, and acknowledgement. This is the introduction. uh, in introduction I tell about what is nanomaterial. Basically nanomaterial are those material which has the range of 1 to 100 nanometric, in that range, and in that scale material exhibit a unique property having great electrical property and having high surface to volume ratio, rather than in the bulk form. So there are some example: carbon nanotube, graphene, metal nanoparticles, metal oxide, and other. So here, this is graphene. Graphene is a single layer of carbon atom which is arranged in the two-dimensional sheet of hexagonal lattice comb-like structure. This is the basic building block of carbon, where it is the allotrope of carbon. There are some other allotrope of carbon which are carbon nanotubes, fullerenes, and graphite as well. By using 3D graphite, we make some one-dimensional layer of that graphene by using graphite. Scientific classification is it is a allotrope of carbon. It has a two-dimensional nanomaterial. It has a sp2 bonded carbon network and having the very low or minimum thickness, that is of one atom, 0.34 nanometer. So here are some properties that make the graphene unique. Uh, a two-dimensional carbon sheet, it exhibits a large surface area. It has a pi electron system, which is very good for the transferring or the electrical conductivity. It is the thinnest and strongest material, and it has a high surface to volume ratio because of its thinnest nature. This is the graphene structure where this is the hexagonal sheet which is arranged in two dimension in hall the in hall of the surface, on the hall surface. This is the carbon bonds in between the hexagonal sheet, and it is sigma bond, and this is the pi bond which is delocalized. So by functionalize the graphene sheet, we can use this for the sensor application and for other biosensor application as well. So what is the role of functionalization in this work? So it provides a specific binding. If we functionalize the graphene sheet to a particular uh, group, then it will trap a particular thing, not other unnecessary elements. This and provide denaturation. It improves solubility and dispersibility in the solvent as well. Enhance signal sensitivity. What is sensor? Sensor is a device which convert a molecule, which convert a event into a measurable signal. So if we have a analyte, lot of analyte, but we want to anchor particular analyte, then we have to functionalize the electrode with a particular group so that it will anchor or trap a particular analyte, and this will give the signal by the help of transducer, either in the form of frequency, time, resistance, or voltage, and other mass change also. So what is biosensor? Biosensor is a sensor which particularly detect biological molecule like DNA, enzymes, protein, etc. So this also work like same like this pattern. Trap the particular analyte and give the signal in the form of frequency, resistance change, and mass change as well. So the research gap is there are numerous study exist on single wall carbon nanotube graphene nanoparticle as well, but there are few rarely explored graphene protein interaction. So we are exploring the graphene protein interaction at the air water interface. Challenges are forming stable monolayer of functional graphene at interfaces, measuring the behavior due to the pH and the temperature variation, limited understanding of shape, its effect on thin film properties. So here we are looking for the air water interface or the change or the behavior change due to protein at the interfaces. So we are driving control uniform film to the substrate or deposit uniform film to the substrate. So why control thin film are essential? It ensures structural uniformity. It improve measurement reliability and hence sensitivity for the biosensor. Enable accurate study of protein interactions. So, what are the solutions? Solutions here in our lab is Langmuir and Langmuir-Bolger technique. Langmuir allows single molecular level control at the air-water interface. It helps in making smooth, stable, and reproducible ultra-thin film. So, what is Langmuir technique? Langmuir-Bolger technique. It is a technique to fabricate ultra-thin film on particular substrate. The substrate might be different according to the application. Amphiphilic molecule, we spread amphiphilic molecule on that air water substrate so that it align according to the their head and tail group to the air water substrate. I will discuss the thing in the next slide with the help of diagram. This is the amphiphilic molecule. Here it is a hydrophilic head group, and this is hydrophobic tail group. Hydrophobic tail group are away from the water surface, and this are in towards the water surface. So this is the Langmuir-Bolger setup. Here, this is the trough. In that trough, we pour deionized water having the resistivity of 18.2 mega ohm. After cleaning the trough by the use of chloroform, ethanol, and acetone, we pour DI water to that trough, and we make sure that the cleaning should be ideally 0 millinewton per meter in the sense of surface pressure. So we measure surface pressure by the help of this Wilmy plate. Wilmy plate is made up of filter paper that is 2 cross 1 centimeter in size, and we hang this Wilmy plate to the platinum wire. This platinum wire is attached to the surface pressure sensor, and this whole setup is attached to the feedback controller and to the LB software. And then by the use of software, we can adjust this barrier as the compression and expansion for the molecule that we spread onto the top of this air water trough. And by the help of micropipette or the micro syringe, we pour our this amphiphilic molecule or the molecule that will show the behavior like amphiphilic molecule or spread or make a uniform layer on the air water interface, or we can change or we can control the temperature with the help of temperature controller onto the this trough. This is the uh, setup of Langmuir-Blodgett experiment, and we can measure here pi a isotherm that is called surface pressure isotherm. So so here, this is a dipping mechanism system. By the help of this control dipping mechanism system, we can transfer our monolayer that the monolayer that we spread on the air water to the substrate. Substrate might be changed according to the application. So there are two type of deposition. This is Langmuir-Blodgett deposition method. Here we use substrate horizontally, and by the use of this feedback mechanism, we can control the barrier compression and expansion like 1 per meter or per minute or 5 per minute of deposition. And this is the second thing, that is Langmuir Sapphire method. Here we use vertical deposition technique. Just touch to the air water surface where the molecule are spreaded, and we just uh, keep it back by the help of LB software or LB feedback mechanism. And In this barrier compression, we observe this graph, which tell about the behavior of monolayer at the air water interface. Like when the barriers are in the expanded form, this show the gaseous phase. When the barrier are in the in some, when we compress the barrier, it will show liquid expand phase, and then again on the compression, liquid expand phase, and then solid. And after more compression, it will show the collapse phase. Collapse phase means the molecular are not on the monolayer phase. Sorry, the molecular are not at in the monolayer state. After the collapse region, it show the 3D aggregation of the molecules. We can measure all the things, or we can look all the things by the help of BAM, that is Brewster angle microscope. So the pi a isotherm is the graph between surface pressure and the area per molecule. The formula to measure uh, pi a isotherm is sigma naught by minus sigma. Sigma naught is the surface tension of pure di water, and sigma is the surface tension with the water with the monolayer present. This surface pressure is also measured by the LB software by itself. It helps us understand how the monolayer changed under the compression of the barrier. So these are some preliminary results that we do in the lab. This is the steric acid isotherm. Steric acid is a long chain of carbon atom having COOH group attached to this. Uh, we measure 1 mg of stearic acid by the help of weighing machine, and then we dissolve 1 ml of stearic acid, 1 mg of stearic acid to the 1 ml of chloroform. The resulted solution is 1 mg per ml solution. Then from that solution, we sonicate that solution with the help of ultrasonication machine, and then we spread that particular solution onto this trough, and we leave this trough for evaporation of chloroform for 25 to 30 minutes. And after that, we compress the barrier with the help of a feedback mechanism of 5 per minute. The graph is like this. This black graph is the isotherm graph, that is surface pressure isotherm, and this blue graph is elastic modulus. Elastic modulus tell about the stiffness of the uniform thing that is organized at the air water interface. uh, this is the polymer result. Polymer, we are trying to make the composition of polymer and graphene or graphene oxide or reduced graphene oxide to for the better enhancement of solubility in the particular solvents. So this is the pi a isotherm, that is surface pressure and area isotherm between the of the polymer, that is called polyaniline. So here we recorded this at the 27 degrees Celsius, and this is the BAM image that we measure at the air water interface, that how the monolayer or the molecule are behaving at the interface phase of water, of DI water. So this is at 11 millinewton per meter, and this is at 24 milli Newton per meter. This is the POM image of deposition of a polymer at particular same surface pressure, and this is at 24 millinewton per meter, a POM image at particular same surface pressure. So this is the setup behavior, how the spreaded polymer is behave like at the air water interface. This is the image which clearly show the nanofiber at the air water interface, and this is the Wilmy plate that is used for recording the same behavior. And this is the FESEM image at low magnification and at high magnification, which is also justified at the fibers are transferred to the substrate. This is the substrate at two different magnifications. These are the solutions, or the different solvent when we use for preparing the polymer. at different concentration and at different dispersible solvent. And this is the 3D printer 3D vial bottle stand which is for creation of printable device for the biosensing application. And these are the results at different temperature. These are the same polymer result at different temperature, at 15 degree, at 25 degree, and 35 degree, and at 50 degree. So in the next slide, we are showing the same result in the compiled form, and these results are showing the gradual change in the isotherm graph after changing the temperature. So this is the compiled result of all these same graph. So at 15 degree, this is at the lower rise of the surface pressure is at lower temperature, and as we look up at the 20, 25, 35, and 50 and 60 degrees Celsius, the gradual increase in rise in the surface pressure is observed due to the molecular randomness. And this is the elastic modulus graph. This blue line represent the isoelastic modulus graph. So this is the peak position representation of elastic modulus graph. So at 25 degrees Celsius, it is showing the good result of stiffness factor of isotherm graph. So here, this is the RGO graph of IV characteristics. Here we disperse reduced graphene oxide in the methanol, and we try to disperse in different other solutions like methanol, chloroform adder, but the dispersibility is good at in methanol. We pour 70 microliter of uh, disperse RGO to the electrode. This electrode is made at the lab by the sputtering unit. First, we sputtered aluminum to this electrode, and then we etch by the laser engraver to make this substrate in the form to make this substrate as an electrode. So this is the IV characteristics that we measure at different voltage. So this is showing the ohmic behavior. The RGO is showing the ohmic behavior. This is the RGO at the interface. So when we try to pour the RGO at the interface, the RGO is not showing good behavior. So we to improve the dispersibility, we use polymer, and we make it synthesized by the help of ODA. So it is not spread properly, and this is like a sand sprinkle particles. Then so this is not showing good result at the interface. So we try ODA RGO. We try to synthesize ODA RGO because ODA has a long carbon chain which make partially RGO like a amphiphilic molecule, partially, not properly. So what we do, we take 1:1 of RGO and ODA,
Ayush, what is full form of ODA?
octadecamyl amine.
Do you have the structure here in any slide of ODA?
No, sir. May I tell? C18H37NH2.
NH2.
Yes, sir.
Okay. And ODA is in powder form.
Yes, sir. ODA is in powder form.
Okay. Go ahead.
Yes, sir. Thank you, sir. We compose RGO and ODA in 1:1. We mix in this in ethanol, and then we do ultrasonication of both in a same vial. Then we transfer this solution to the beaker, and in that we do magnetic stirrer for 24 hours, 500 rpm at 40 degrees Celsius. And then after that we transfer whole solution to different small vials for the centrifuge, and we remove extra ODA that was bind to the RGU by the help of centrifuge at the rate of 7,000 rpm for 10 minutes. After that, we get a ODA RGU solution which was not confirmed yet, but after the few characterization, we confirmed that this is showing the attachment of OD and RGO. Then we do, uh, and we heat to the high temperature oven machine at the 80 degrees Celsius for 12 hours. So this is the result of ODA RGO, and the right side results are only GEO, that only GEO results. So here, this is the result which was sent by the commercially purchased RGO unit, and this is the result that was done at the BITS campus Cal facility. So this peak, this is at 300. I intensity of D peak is at 300, and the intensity of G peak is at 1500, approximate 1580. So after calculating the ratio of ID and IG, it is equal to 1.5. So the ratio is showing that at 1.5 ODA is attached to the RGO, because if the ratio is ID by IG ratio is 0, that means the compound is pure. And if the ratio is little bit above, like 0 to 0.5, then it show that a GO is present. And to that, if the ratio is 1, then this is show RGO is present, and to the above, this is show some long carbon chain is attached to this show. According to the literature review, we confirm that
Ayush, can
G.
you repeat what you have said about DNG bands of Geo? On the right hand side, you have the commercially purchased RGO Raman spectrum. On the left hand side, you have what you have prepared in the laboratory with the ODA addition. So
Yes, sir.
if your D in your case D band is of higher intensity, whereas in the commercially purchased it is almost equal to that of G band.
Yes,
So
sir.
if the intensity of D band is increasing, what does it mean?
Sir, if the intensity of D band is increasing, means defect is increasing. Here, the defect is in the form of CH group. That means carbon chain group, long alkyl chain group. So this show, if the ratio is equal or higher to the 1.5, then this show long alkyl chain is attached to graphene or reduced graphene oxide.
About this ratio ID by IG, you have mentioned that if ID by IG is 1, then it would be GO, not RGO.
No, it is geo when the ratio is 0 to 0.5 or 0.7, and
Less than zero point 0.5.
approximately less than zero point 0.5. Yes, sir.
Then you will say it's a GO.
Then it is geo. Yes,
If
sir.
it's going above 0, above 1, then
Above one, show that some long alkyl chain or some carbon molecule and other different defect are attached to the RGO. Sir, this is by mistake I written here geo. This is RGO here.
this is RGO. Okay.
Sorry, this is by mistake written here geo. ODA, RGO, and RGO. The comparison, the right hand side is RGO.
Okay. Okay, please go ahead.
Uh, so this is the FTR spectrum with the peak detection of same ODRG, and the company measured RGO. So here these are some peak which determine this attachment of ODA to the RGO, reduced graphene oxide. So this is due to stretching. This is CH2 asymmetric stretching. There are two CH2 stretching. That is, if the stretching is in the same direction or showing same behavior, then this is symmetric stretching, and other is asymmetric stretching in the opposite direction. And here this is NH2 bending. NH2 bending is also in two or three more form. Caesar form, rocking form. Caesar form, in the Caesar form, the molecule is uh, oscillating, hydrogen molecule is oscillating in the same direction. But in the rocking state, it is this is like a chemistry part, not a physics. But sometimes the rocking is like the hydrogen bond is in the right, in first is in the right and second in the left, the opposite direction, and this is due to CNH stretching. This is the TGA curve, where at the right hand side, because the graphene and the reduced graphene has the property sorry, the reduced graphene has a property that it can adopt, or it can be constant at the temperature 400, at 500 or 550. But here we can see the temperature is by the increasing temperature, the weight is breaking. So at the 150 degrees Celsius, the weight of the ODA RGO is decreasing because of alkyl chain of long carbon atom. So here this is breaking at the approximate 500, or here it is breaking at the 150 or before 200. So this is the paper that I present at the NIT Uttarakhand. This will publish approximately October 2026. This is the Springer proceedings, and here I got a uh, best paper award at NIT Uttarakhand of the title Investigation of Polyaniline Langmuir Blodgett Film at the Air-Water Interface. These are some references, and this is the acknowledgement part. I express my sincere gratitude my supervisor, Professor Rajkumar Gupta sir, Professor Department of Physics, BITS Pilani, for his continuous guidance and support and for motivation. I extend my heartfelt thankful to my DAC members, Professor Manjula Devi V, Head Department of Physics, BITS Pilani, Professor Naveen Singh sir, Professor Department of Physics, BITS Pilani. I would also like to acknowledge Professor Rakesh Chobisa sir, DRC convener, for his valuable suggestion and support. I am also thankful to head of the department, physics, BITS Pilani Pilani campus, lab members, and my colleagues for their constant support and encouragement. And thanks to NRF project for funding, and thanks to BITS Pilani Pilani campus and Rajasthan. Thanks.
Yeah, so Professor Rahul, now it is open for questions.
Ayush, nice work done by you in last 2 years.
Thank you, sir.
Because it's a JRF to SRF conversion presentation, so I guess that you whatever you have done, that is for the last 2 year work.
Yes, sir.
So one thing, I have a few questions.
Yes, sir.
Let us go one by one.
Yes, sir.
First, about you have obtained a good knowledge about your LB setup.
Yes, sir.
You have explained each thing about LB setup very carefully.
Yes, sir.
Uh, my question is that in case of RGO, it is well known that it's not so easy to prepare the thin film of RGO. If you will not get a very good suspension of RGO part, and that's why you have added another group, which was, I think, something AGO. You have added. You have added into it.
Yes.
So first thing is that in your LB setup process, you are making the thin film of mono layer.
Yes, sir. Yes,
Okay.
sir.
So how you are sure that whatever, like after dipping your substrate into the turf, whatever is coming on the substrate, how you will make sure that it's mono layer?
Sir, by the characterization, by the either we can characterize by the help of ellipsometry or XRR, so that it will confirm the monolayer is in nanometric scale, or if the some molecule are at nanometric scale, this will show the properties of monolayer, because
Uh,
atom size is approximate 0.36 0.34.
yes. So you are saying by ellipsometry or by XRR?
Yes, sir.
Okay, you may go through it again, and how you will make sure that it's a mono layer, and because you are working in a thickness region which is less than 1 nanometer.
Yes,
Okay,
sir.
so it's not so easy to find out the exact thickness or the monolayer formation.
Yes, sir.
Okay, so can you come to your slide where you have shown this Raman spectrum and other spectrums of your RGO plus ADO?
Yes, sir. Sir, this is ODA
ODA.
RGO.
Okay. So you have added ODA only to enhance the suspension of your RGO solution, RGO in solution solvent, methanol?
Sir, here we use ethanol for the dispersion of
Yeah, doesn't matter whether it's a methanol or ethanol, but you have used ODA only to make it dispersible.
what's that?
Why you have added ODA?
Sir, because to make this molecule dispersible and for making the thin film at the interface, because here alone RGO is showing wrong behavior at the interface. This is like a uh, the sand. This is showing the behavior like a sand particle, as we can look here.
After
So
after adding ADO,
yes,
uh,
sir.
were you able to have this thin film of monolayer of RGO over substrate?
Yes, sir. Sir, because that was reported in the uh, a paper of Professor Rajkumar Gupta, sir, that after uh, uh, functionalized to the ODA and RGO, ODA and GO with ODA, it will show the behavior, a good behavior at the air water.
Yeah, okay, it's a very interesting work. I'm getting keen interest in this. My question is, after adding ODA and after preparing the thin film over your substrate, your
Yes, sir.
film is having RGO with ODA.
Yes, sir.
But how you will make sure that this film, the properties of RGO is not getting deteriorated due to the presence of ODA?
Because sir, here as we look the peaks D and G peaks, D and G peaks itself define that RGO graphene is present because this D and G peak is due to graphene. So here the property is not that much lost here because of these two peak clearly show the D band and G band, and which is come to the graphene only.
So you may again read carefully about the Raman spectrum of different carbon allotropes. It will help you to understand more about this graphene RGO structure. D and G bands are the characteristic of the amorphous carbon, and
Amorphous,
you
yes.
you take any allotrope of carbon, whether it's a fullerene, whether it's a amorphous carbon, whether it's a CNG, whether it's a graphene RGO, you will always get these DNG bands. Okay.
Okay, sir.
D means it's a, if we are getting D means D peak, it means there are some disorder in our films, and if we are getting only the G peak, it means it's pure graphitic ordering. Okay.
Okay,
So
yes.
to get the DNG peak in your Raman spectrum, it doesn't mean that you have the RGO in your sample. You may have different like amorphous carbon also, or maybe let's say 20% RGO, 80% amorphous carbon. There may be many things. Okay.
Okay, sir.
So
Yes, sir.
it will help because it's very interesting for Raman, for carbon allotropes. Raman is the most sensitive tool to understand the properties of the carbon allotropes. So you may again go through it, although it's a very interesting work.
Okay, sir.
And can you go to your TGA slide?
Yes, sir.
In TGA slide, you are showing in the right hand curve, which is basically for the commercially purchased RGO sample. You are
Yes, sir.
getting a almost 90% weight loss around 620 or 650 degrees Celsius.
Yes, sir.
What is the reason of it?
Sir, because of breaking of the bonds between the graphene sheet.
Then how the weight would be reduced?
Because uh, when the bonds are broke, then the carbon atom are not that attached and the shrink to the sheet to the bulk, the kind of material.
But the weight is only due to the carbon atom. The bonding doesn't have any weight. If we are seeing weight of the material, it is only the weight of the atoms.
Okay.
So my
Sorry.
question, why I'm asking is
Yes, sir.
whether some RGO is evaporated at 640 degrees Celsius. The weight loss is due to that reason. It is obvious that bond would be breaking after 600 degrees Celsius. RGO would lose its properties. You will get the amorphous carbon in your sample. But weight loss is only due to the breaking of the bonds, or weight loss is also due to the evaporation or sublimation of some of your material.
Okay,
So
sir.
that you may again go through and you can read it again.
Okay, sir.
And my last question is, you have done very interesting work. This technique is very very interesting. Why I'm saying it's very very interesting? I have used two times this word very,
Okay, sir.
because it's not so easy to work with a ultra thin film. Okay,
Okay, sir.
and you are even not working with ultra thin film. You are trying to work with a single layer, monoatomic layer.
Yes, sir.
It's most difficult part because handling of these mono layers are not so easy.
Yes,
And that's why I think I can guess that because you have already completed 2 years. 1 year was for your coursework, and second year you did some experiment.
yes, sir.
But it seems that you should have done few more characterization or some more work in the last 1 year.
Yes, sir.
But again, I'm saying it's not so easy to work with the ultra thin film, monolayer films. That's why I think you couldn't do much characterization or much work in last 1 year.
Okay. Yes, sir.
Okay. Other things is okay. My best wishes to you. It's very interesting work. Please work hard, and whatever you have shown in your objectives, like you want to attach some protein with the RGO,
Yes,
and
sir.
that is to make a biosensor. So,
Yes.
so what is your plan? How you will attach the protein with the RGO?
Sir, first we try to use the protein in the subphase here in the subphase, and we try to change in the pattern of isotherm. Let us suppose here this is the A pattern without using the subphase graphene, and at after using the graphene protein in the subphase, let us suppose we are getting B kind of graph here. This is just a demonstration. Let us suppose we get a B kind of gram, then we use our substrate for deposition, and we try to use that particular substrate in the QCM or in electrochemical technique.
And which kind of proteins you would be using?
Sir, BSA, HSA, HA, and other.
Okay, that's really good, Ayush. And because you are working on biosensors, which has technological importance as well, and whatever work you will do in these biosensors, I'm sure you would be able to publish in very high impact factor journals.
Thank you, sir.
And I just suggest you to work hard, work more for your research problems.
Yes, sir.
And the field is very interesting. You have gained the knowledge about the LB setup also. Everything looks nice. Only thing is that you have to perform few more experiment to try to get obtain more experimental data, and do more analysis part.
Okay, sir. Sure.
Yeah, thank you. Over. It's over, Professor Gupta. It's over from my side.
Okay, thank you, Professor Rahul. Uh, Professor Manjula Devi, no, Professor Rakesh.
Hello.
Yeah, I think I have been interacting with Ayush, so it is fine for me.
Yes, ma'am.
Yeah, one or two comments from my side, like uh, that some of the terminology that you have used are not scientific, Ayush. So
Okay, sir.
you are at the highest level of securing your degree, PhD. So
Yes, sir.
you should not talk in the colloquial language. You should be scientifically precise when you are making a presentation or writing a draft or something. Colloquial, you can say whatever it is, but when we are making a presentation, scientific term should be in the proper form. Okay.
Yes,
So
sir.
second thing is that when you do some analysis, when you perform some experiment, uh, proper analysis is also, is an integral part of that experiment. The data
Yes.
is seen, but after collecting the data, the analysis, to understand about the system, that is also very important to know.
Okay,
So
sir.
UKG says that these people are that people, but what that physically corresponds to. If you come to know about those things, then probably it will be very easy for you to communicate the proper sense to the audience. So that is it. Third thing is that, as Professor Rahul mentioned very clearly, that some more work is expected from you because you're working in the past year. Let's say that 1 year is already have accessibility was always there with you. Okay. You have taken sufficient time to get acquainted with the system. So now still 3 years are there. So what we suggest is that it's your thesis, right? So
Yes.
put it into it, work properly and sincerely, and try to get what
Okay.
So are there any other questions or suggestions? So Professor Rahul, are there anything to come?
Yes, yes, it's okay. We can recommend his status from JRF to SRF if all committee members agree, and with the suggestion that he may make more, perform few more experiments, try to get more analysis part, especially in Raman and other things.
Okay, sir.
Yeah, otherwise it's okay. We can recommend him.
All right, Ayush, thank
Yes,
you
sir.
and special thanks to Professor Rahul for taking his time and assessing for this GRF result. Thank you all the committee members, Professor Rakesh for his special thanks a lot.
Thank you.
Thank you, sir.